All right, on this podcast, we'll be talking about molecular, ionic, and net ionic equations. So, just to kind of recap on solution notation, remember that for solutions, it's important to understand what state they're in. So, something that's considered soluble, which means that it breaks into ions, we write them as aqueous. So, here we have ammonium nitrate, we dissolve it in water, and it forms two ions, ammonia ions and nitrate ions, and we write that by the aqueous here. An insoluble compound is when you mix some stuff together and it forms a solid in the reactant product side. So here we have potassium chromate aqueous reacts with barium nitrate solid. We dissolve these in water. We form barium chromate solid and potassium nitrate, and that remains aqueous. So this is insoluble because this is in the product side and it formed a solid. All right, so let's get into this. Molecular equations are pretty easy because you should know how to balance equations. It's not anything different from what you've been doing. The only difference is you must put what state they're in. So this one's an aqueous state, which means it's again dissolved in water. Silver chloride, sorry, not silver chloride, sodium chloride is aqueous. Silver chloride here forms a solid, and then sodium nitrate is aqueous. So the only difference between what you've been doing is that you have to put what state they're in for each one. And that's how we define a molecular equation. The problem is when we deal with solutions is that a molecular equation doesn't always tell us accurately what's going on, and people might get the wrong impression of what's going on. So let's take this example of this molecular equation. We're going to react potassium chloride, an aqueous solution of potassium chloride, with an aqueous solution of silver nitrate. They will mix together to form potassium nitrate and silver chloride, but the silver chloride will precipitate out. So here we have an inherently well, not wrong problem, but people might get the wrong impression. So I'm going to break it down to you visually. So when we look at this, potassium and chloride are not together in solution. They're actually as ions, represented by this picture. Nowhere in this picture are actually the potassium and the chloride ions together. Silver nitrate, same case. The silver and the nitrate ions are actually ions in solution. They do not actually are physically together. And these two pictures represent each, and they look colorless to you because they're each as ions. When you mix the two solutions together, all the ions begin to mix. So now you have four different ions combining, and what eventually happens is that the silver and the chloride ions will actually combine and form this white precipitate here on the bottom, and whatever's left over, the silver and the nitrate, will remain as ions in solution, which is represented by this. So molecular equations are easy to look at, but what's going down on a molecular level, sometimes you may get the wrong impression. This leads us to the next definition, and that's called net ionic equations. I'm sorry, not net, complete ionic equations. In a complete ionic equation, we write them basically as how they really are, and that is as ions. So if you notice here, in a complete ionic equation, all strong electrolytes shown as ions. So just like they really are in the solutions, we write them all as ions. But the only difference is that when the solids that stay together, we keep them together. So in a complete ionic equation, again, we write them all as ions, but anything that forms either a solid or sometimes a product can be a liquid. If you see any one of those, you keep them together in the product side. You do not break them up. And this would encompass a complete ionic equation. Right. Okay, the ones that did not react, we call these spectator ions. So spectator ions are ions that do not participate in the reaction and remain in solution. So if you notice here, the potassium stayed as a aqueous, it stays as an aqueous in the product side. Nitrate is aqueous here, it stays as aqueous over here. So these two got ions, we call them spectator ions. They are not participating in the reaction. So just as the term goes, if you're not a part of the solution, you're part of the precipitate. So when you're done laughing, you can go to the next slide. The last term is called net ionic equations, and net ionics only show what's actually forming, either a solid or a liquid. Everything else are spectator ions, and we do not include them in the equations. We actually take them out. So just like the example I've been carrying through, all spectator ions are removed, and all we care about are those ones that remain behind. So let's try a few examples and see how you do on writing these. Whoops. All right, I would like you to try this. Write the molecular, complete ionic, and net ionic for the following reaction. A sodium hydroxide solution is mixed with an iron 3 chloride solution. You're going to have to predict the products, balance it, and then write equations for each. So go ahead and click pause, try this, and then we'll go over it as soon as you're done. All right, so what you should have done for your molecular is sodium hydroxide reacts with iron 3 chloride to form sodium chloride and iron 3 hydroxide. And that is the one that actually precipitates out. Everything else is aqueous. You should have also balanced it, so just don't forget your coefficients here. So in a complete ionic, we write everything as ions. Since we have 3 sodium ions, that's going to be represented here, 3 sodium ions. We have 3 hydroxide ions. We write them separately, 3 hydroxide ions. We have 1 iron ion, and we have 3 chlorine ions, but we have to put the 3 in the front. So that's where we don't write the 3 in the bottom as a subscript. It's written in the front. We form 3 sodium ions and 3 chlorine ions, and then the solid stays together. So this will be the correct way of writing a complete ionic equation. All we care about are the net. For the net ionic, we want to get rid of our spectator ions. So all we're left with is hydroxide plus iron produces iron 3 oxide. And it's written as this, net ionic. If there are any coefficients in front of these, if there were, you would get rid of them or reduce them down to the lowest common denominator. So let's try one more example and then we'll call it quits. So try this equation out. Go ahead and click pause, and then we'll go over it in just a second. All right. Silver nitrate solution is mixed with a potassium chloride solution. So this should be your balanced equation that you've gotten. All states are there. What forms a precipitate is the silver chloride. The complete ionic is when you break them all into ions except for the silver chloride. So this is what you should have gotten. And the net ionic is all the ones we only care about. So in this example, the silver and the chloride are the only ones we care about. We bring it down. That is a net ionic equation. All right, that concludes this podcast.